Today we're going to look at the history of atomic structure. We're going to look at some of the models as they were earlier on in our understanding, and then we're going to take a look at how the models that we have of the atom changed over time and the reasons that they changed. And they changed really because further experimentation was done every time somebody proposed a model, and the results of those experiments very often were used to conclude that the previous model couldn't be as it was supposed to be, and so then a new one was proposed. So that's what we're looking at today. So we're going to compare the models of the atom, we'll explain why ideas have changed over time, and then evaluate different models of the atom. So first of all, I've got J.J. Thomson written here, but if we start a stage before that, there was a British scientist called John Dalton, and he'd argued that everything in the world was made up of these impenetrable, indestructible spheres. They were likened to billiard balls or snooker balls, and they were thought to be absolutely tiny, and he called them atoms. And for a long while, that was the accepted wisdom, that, you know, if you cut things down into small enough size, then all you would find are hard, indestructible spheres, balls that everything was made of. But then towards the end of the 19th century, a guy called J.J. Thomson, he did some experiments. He actually discovered the electron. He was looking at low pressure gas sealed in glass tubes, and what happens if you put a high current across it. And basically he managed to make this visible stream of particles. And he noticed that if you put a positive charge near these particles, it attracted this stream of particles. So that told him that these particles, whatever they were, must be negatively charged because they were attracted to a positive charge. And he called them electrons. So what he proposed by looking at the movement of these beams was that actually atoms were made up of these negative charges, these so-called plums here in his plum pudding model. But he also knew that atoms overall had no charge. So he thought, well, these negative charges must be cancelled out somehow. And so he suggested in his plum pudding model that these negative charges were embedded in like a less dense overall positive charge. And so the plum pudding model was born, and for a while that was the accepted model. Until another British scientist, Ernest Rutherford, he started to look at what happens. He was testing the ideas that J.J. Thomson had put forward, and what he was doing was making gold foil absolutely as thin as he could, and then firing alpha particles at it, which are positively charged particles made up of 2 protons and 2 neutrons, the same as a helium atom. And he expected, because he expected there to be so far the plum pudding model, he expected that all of these particles would just fly straight through the gold foil, because the plum pudding atoms were supposed to be just a thin, positively charged, almost like gas with the negatively charged plums inside them. But that isn't what he found. What he found actually is some were deflected, some would change course slightly, some would change course a lot, and some even bounced back. So if I show you a little simulation of what they would have expected to see if they were looking at the plum pudding. So here is a representation of the plum pudding. So we've got our red positively charged diffuse area, and then we've got these little negative charge in it. And if I turn on the alpha source, this is what we'd have expected to see with the plum pudding model. All these alpha particles just sailing straight through. But that isn't what we saw. What Rutherford actually saw was something like this. So here the alpha particles are a bit smaller, these purple things, but you can see how some, as they go close to the nucleus, are being deflected and bent off course. And that's because he discovered that the nucleus must be positively charged, and it must be quite dense, because it's got enough in it, enough mass to be able to deflect and even occasionally bounce back these positively charged particles that are being fired at it. And it must be positively charged because it's repelling these positively charged particles. And of course, positive charges, or any like charges in fact, will repel one another. So if we zoom in a little bit more, you can see what's happening here. These positively charged alpha particles that are being fired at it, when you come near to the nucleus, they do get repelled, or they get deflected off course. And that's what Rutherford saw. And really what that told him is that, okay, we mustn't be the plum pudding model, we must have an atom with a nucleus. Because most of them did go through, he proposed that, yeah, the atom is mainly empty space, because most of these alpha particles do go through, but there must be a concentrated positively charged nucleus to these atoms, and so the nuclear model of the atom was formed. And about 10 or so years after that, or a few years after that, Niels Bohr, who was another physicist, he developed the idea a little bit further. Okay, so he agreed that there should be a positively charged nucleus, and he also agreed that the electrons would orbit around this nucleus. But then he did various experiments on atoms emitting light and thought, okay, atoms of the same element always give out the same amount of light. And what that actually said from his experiment is that they're not just randomly orbiting the nucleus, the electrons, they must be orbiting in set energy levels. Okay, so whereas in Rutherford's model we had a positively charged nucleus, which we still have here, and then just electrons orbiting freely around the nucleus, in the Bohr model we've still got our positively charged nucleus, but then our electrons are arranged in set energy levels, or shells as we call them. Okay, so it developed further, and this really is the model that we're familiar with today. There were further experiments done, because even after all these experiments we hadn't really conclusively proved the existence of neutrons, but there were experiments done subsequently which did confirm the presence of neutrons, and they were said to have the same mass as a proton but no charge. Okay, so what I want you to do in your books is you can just put a cross across a whole page like this, to split it into 4, and then have the Bohr model, the nuclear model, and the plum pudding model. And I would like you to use the information from the preceding slides, and also you can use the internet again. You want to pause this video and fill out some information on each of the models. So what I want to see is, who were the scientists involved in suggesting these models? What experiments did they do that led them to suggest these models? And I'd like a simple diagram of each of the models, the Bohr model, the nuclear model, and the plum pudding model as well. Once you've done that, you see timelines in the bottom order. You can just put the scientists or the discoveries in chronological order there, but on a separate sheet I've attached a timeline for you, or you can draw your own. Just let's have a timeline, a line drawn across the page with the years where these discoveries were made, and that should really clearly demonstrate how ideas about atomic structure have changed over the course of time. Okay. All right, hopefully you've completed that task from the previous slide. What you're going to need to do here is pause the video again in a second and then answer these questions. So have a look at the information that you've got on your information sheet about the different models, and then look at what are the differences between each of these models, and are there any similarities between the models. And then finally, once you've done that, look at the models themselves. You probably use your simple drawings for this, and decide which do you think would be most useful for learning about trends or patterns in the periodic table. Okay. Once you've done that, I would then like you to complete this evaluation of the 3 types of models, so the plum pudding, the nuclear, and the Bohr model. What's useful about it? Because even though we know that atoms are not structured in the way that the plum pudding model suggests, there is still some usefulness in that particular model. For example, that it accounts for the negative charges in an atom. But for each of them, what's useful about it? What's its limitation? What does it not really explain? Okay. So see if you can complete that. The hardest one to do is probably going to be this one, and I always use the analogy, if you think about an atom really as being a football stadium, with the nucleus being a football sat on the centre circle, sat on the centre spot ready to kick off, then the electrons would be like peas floating around the stands. Okay, now that helps you to appreciate just how much of the atom is actually empty space, and the nucleus only makes up a very tiny amount, tiny part of the atom. Whereas any of the models that we draw, just because they're usually limited for space on the page, don't really take into account quite how much of the atom is empty space. So that might be something that you might put here for something that it doesn't help explain. Okay, so pause the video here, complete these questions in your book, and copy and complete this table in your book as well, please. All right, here are some of the answers that you might have put. These are not going to be the only answers. There are other things that you might put as well. But if you want to pause the video here, you can mark what you put. That's just been cut off there, but that does say the Bohr model It's the one that's the most useful for us learning about trends in the periodic table. That's because obviously the group that an element is in tells us how many electrons it's got in the outer shell, and with the Bohr model we have shells, we have energy levels, and also the period that an element is in tells us how many shells it's got. So the Bohr model with its shells obviously tells us that as well, and that's why it's the most useful one. Okay, finally, to finish then, one more pause, have a go at these questions. Why do scientific ideas change over time? And give 4 reasons why new ideas are often rejected at first. And some of those, think a little bit outside the box though. So it might be religion, it might be lack of evidence for new ideas. It might be that people are reluctant to change their ideas, especially if they've invested time and effort in a different idea. But see if you can have a go at those questions. Pause the video again here. Okay, and here are some of the answers that you might think about putting for those. And there are going to be other ones as well, but those are some of the main ones. All right, finally, if you could have a go at this for me, please. So it doesn't really matter too much which order you do these 3 in, but it is going to help us tie together and think about everything we've done in this lesson. For a final time, pause the video here, have a go at these 3 questions, and then I will have a look at those in your book once I get them back.